Okay, so this video is going to cover section 9.2, which is all about the properties of chords. Now, chords have a lot more properties than tangents do, but the nice thing is a lot of them are kind of things that you've seen before and aren't going to be too surprising. Some of the tangent ones you might have not really thought about before, but I don't think these are going to be ones that are going to come as too much of a shock once you see the pictures. Before we start, just a quick review on some of these definitions. We have talked about the word central angle before. And so here they've got some pictures. Central angles here include angle AOB, which is this angle here. It includes angle DOA, which is this angle here. And it also includes angle DOB, which is this angle here. What you'll notice is all three of those angles have a vertex of the center of the circle. And the other points are on the circle itself. Things that are not central angles, pretty much every angle in this picture is not a central angle. None of them have the P as the vertex. And so the definition the book gives is central angles is an angle that has its vertex at the center of the circle. That's all it is. They could draw these to continue out past the circle. That wouldn't be a problem, but the vertex has to be the center. That is the big deal. Next thing we've got is what's called an inscribed angle. An inscribed angle, if you take a look here, angle ABC is one of them. So from A to B to C, that's this angle here. BCD is one of them. This angle here is a inscribed angle. And CDE, this angle is an inscribed angle. And things that are not. PQR, well, that's up there. It's outside the circle. STU, well, that's a central angle. So we already knew that was something else. And VWX, you can kind of see it has some similarities. Its vertex is on the circle, but then X is a point outside the circle. So a definition for an inscribed angle is a central. That is not the right definition. Just a second here. We'll get this figured out. Okay, and we're back, hopefully. So I went ahead and fix that. An inscribed angle has its vertex on the circle, and its sides are chords of the circle. So you can see the reason that this angle here, VWX, didn't work is WX is not a chord of the circle. DE and CD, those are both chords of the circle. And so basically it's an angle that's kind of formed like you would imagine an inscribed polygon to be. All the angles of an inscribed polygon are inscribed angles. And so we'll find out something pretty interesting about inscribed angles and arcs in just a second. So first up, we've got the chord central angle conjecture. You've got a picture here, and I bet you could figure out this one. It says if two chords in a circle are congruent, then they determine two central angles that are what? And that's talking about what do you think you know about these two central angles? Now we've got an exploration here, but maybe you think about what you might think those angles would have to be. I'll go ahead and open this up. Wait for it to load and then pull it back over here. So here we've got the same exact picture, just in a dynamic situation or dynamic setup here. And so if we take a look, you can see I can change these all around, but I've made it so that those two chords always stay the same. Now let's take a look at the central angles. You'll see here they're the same. If I change them, ooh, that's not good. It broke. Why did it break there? Ah, that's weird. My thing came disattached. You can see if I don't let it break, you can see there it's staying the same. So you can see there, always staying the same as long as I don't let it break and come disattached. So central angles, they're going to be congruent. And that should make sense. If you think about this in terms of congruent triangles, that should be something you could prove pretty easily. We've got these two sides already marked congruent. Well, all of these sides are radii. And so if you look in these two triangles, we've got side, 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 congruent to side, side, side. So we've got congruent triangles. The angles definitely have to be congruent as well. The next conjecture actually uses the exact same idea here. It says if two chords in a circle are congruent, then their blank are also congruent. You can see in the picture they're looking at those arcs. And we just talked about how if the chords are congruent, the angles are congruent. Well, the arcs are just determined by the central angle. And so we'd say they're intercepted arcs are congruent as well. And again, that one shouldn't be too surprising. If we already knew the angles were congruent, then by definition, the arcs have to be congruent as well. Next up, we've got the perpendicular to a chord conjecture. And this one says the perpendicular from the center of a circle to a chord is the blank of that chord. So I've got my two chords, and really only need one here. And I'm drawing a perpendicular line that goes from the center perpendicular to the chord, and it can go out, it can stop, whatever. Well, let's take a look at this one. We'll get this to load up here, and then bring it on over. So here I've got a chord. You can see I can move the chord however I feel like. It always stays on the circle. And I'm going to go ahead and construct the perpendicular to the radius. And then we're going to look at these two pieces from B to the center and C to the center. And you can see they are equal. It doesn't matter how I move this piece around. If I go past there, it obviously breaks, but it doesn't really matter there. I can make the circle bigger, I can make the circle smaller. They always stay congruent to each other. And so the perpendicular from the center of a circle to the chord is the bisector of the chord. Means, remember, if you remember the word bisector, means it cuts it in half into two equal pieces. And so if you wanted to put a picture down, and a picture is a good thing to have written down on these, you could go in and put congruent marks on those. And one thing to note is these are the radii, right? These are drawn as rays that keep going, but they are also radii if you were to stop them there. So a radius is a perpendicular bisector. If a radius is perpendicular to a chord, it's also a bisector. A couple more here. I think we only got two more. The chord distance to center conjecture. Two congruent chords in a circle are blank from the center of the circle. So let's go ahead and pull that one open here. There we go. So I've got, in my picture here, I've got two congruent chords. You can see that they should always stay congruent no matter what I do. And you can see that one breaks as well, doesn't it? Not sure what I did wrong there. But, oh well, we'll make it work. So if I put in the perpendicular segments, and then I show the measurements of those segments, you can see that the lengths of those segments are equal. And assuming I can move it in a way that doesn't break my circle, you can see that no matter what, they stay the same. And so the word for being the same distance from the center is equidistant from the center. If you want to just put in the same distance, that would be perfectly fine too. Nothing special about the word equidistant, it's just the word that you'll hear in math. And then we've got one final one here, the perpendicular bisector of a chord conjecture. This one is actually the exact, basically the exact converse, probably a word you maybe not remember, not very familiar, but it's like the exact opposite of this conjecture that we talked about up here. Here we said if a perpendicular from the center goes through a chord, it's a bisector. Here we're asking the question, if we have a perpendicular bisector of a chord, what do we know about it? Well, I'm just going to go ahead and draw one of these in here. If I draw the perpendicular bisector of this chord, you'll see it goes straight through the center of the circle. Change colors there. And then if I go and draw another one, the perpendicular bisector of this chord, you'll see it goes straight through the center of the circle. And so it's the exact opposite, or the kind of the other way around of the one we talked about earlier. The perpendicular of bisector of a chord goes through the center of the circle. And like I said, if you knew the first one, this one hopefully didn't seem all that shocking. It's just a continuation of the one we talked about up here. And so those are our conjectures that we've got. There are 1, 2, 3, 4, 5 of them total. And hopefully there's actually going to be a couple of things that you're going to learn in the homework that we haven't talked about yet too. So a couple of questions here. So let's take a look at these summary questions here. So one of the conjectures we learned is that congruent chords are equidistant from the center. What do you think we could say about the distance from the center if one chord is longer than the other? This might help draw a picture. Draw a circle with a longer chord and a shorter chord and see what do you think. Is that always true? And so it turns out the longer chord, because it's closer to being the length of the diameter, actually has to be closer to the center of the circle. Smaller chords will be further away from the center. And then the second question here, what's needed to ensure that two arcs have the same shape and size? So the first thing we're going to need is we've got to know that it's in the same size circle. The radius of the circle has to be the same length. If one circle is bigger or smaller, you know they're not going to be the same. The second thing is you're going to have to know that the central angles are congruent. If the central angles are congruent, you're going to know that the arcs have the same size. Now, what we learned today is that if you know that two chords are the same length in a same size circle, that's good enough too. If you know that two chords are the same distance from the center of the circle, that's good enough too. So there's a couple of different things that are the same thing as knowing that those central angles are congruent. Okay, a couple of examples here. Here we've got some information. This would be a good one if you are doing this at home. Draw this out on your paper and then fill in the stuff that you know. And then see if you can find what is CAD and what is side DB going to be equal to. Okay, so let's go ahead and think about this one. So we've got AB is 14. That is this whole thing. We know that arc AB is 110. And so we are supposed to find angle CAD. So C to A to D, that's this angle here. And we're also supposed to find DB. So a couple of different things we could start off with. One thing we could do, if the arc is length 110, we know we can just move that into the angle. So the central angle is 110. I'm going to change colors on that so it's easier to read. From there also, we've got radii. So we know that these two angles in the corners, angle A and angle B, are the same as each other. So that would be something else we can know because this is an isosceles triangle. So we could do 180 minus 110, and that's equal to 70. And then since we have to split it up equally in both sides, we've got 35 and 35. So 35 for this corner and 35 for that corner. And that means that CAD, the one we actually wanted, was 35. Then we've got DB. DB here is this section here. Now here's the deal. We've got a chord and we've got a perpendicular from the center. Well, that means that it bisects this segment. We know that these two pieces are equal. So using that conjecture that we learned today, those two pieces have to be the same. If the whole thing's 14, then we've got 7 and 7. And then the last one here, this one uses a little bit of algebra. So we've got two chords, A, B, and C, D, that are congruent, and we want to find x. Well, the deal here is if these two chords are congruent, well, that means that these two distances from the center have to be congruent. So we can write our equation. 2x plus 6 equals 24. Well, we can subtract 6 from both sides, so 2x equals 18. And then we can divide by 2, so x equals 9. So a little bit of algebra in there, always a good thing to review. Now the homework for today is going to be a little longer. It's 10 questions instead of the 5 or 6 from yesterday, because there are a few more conjectures in here. So the first 3 or so are pretty straightforward, I think anyway. Make sure you're spending some time on the rest of these though. Draw the picture out. Think about the things that you know. If you know that AB is congruent to CD, well, what's that tell you about PO and OQ? Can that help you solve that problem? Here, think about what you know about things like a half circle, or even just like a straight line, or the two radiuses, things like that. You can start to fill in different pieces. One thing I do want you to look at is compare on number 5. Compare these two numbers. Measure of arc AC and angle B, the inscribed angle B. That is going to be something that is very, very useful to know that rule. Same thing here. You've got a lot going on. But if you start to draw in the things that you know, marking the things that you know, you're going to be able to figure out what X, W, and Y are. And then the last one you got to do is a what's wrong with this picture. So just in words, describe why this picture is not possible. Okay, so that's what you've got to try to do. The answers to all these are in the class notes down below where you clicked on this video in Canvas. So take a look at those, and I will see you hopefully soon.